Okay, Lorraine, we are live on YouTube.
Okay, I'll start.
Okay.
Welcome to Dr. Jeff Dusek's presentation on robotics and ocean engineering. Thanks for joining us today from all over the world. It's really incredible to see all of you. My name is Lorraine Leo. I'm a former teacher of technology and one of the coordinators of this presentation. I'm logging in from outside of Boston, Massachusetts. I'd like to introduce you to the co-coordinator of the presentation, Manjula Gayan from Sri Lanka. And I'd also like to thank him for creating the wonderful posters for the program. Manjula?
Yeah, Lorraine, thank you very much. So thank you very much for joining us today. And my name is Manjula, and I'm a teacher of information and communication technology at Pahan Institute of Language and Technology in Ampara, Sri Lanka. So I will give you a quick overview of Jitsi Room. So you will find the chat box on the lower left during the presentation. Feel free to text question for Jeff into the chat box, and he will answer them when he's done with his presentation. And keep your microphone on mute and keep your headphone on. If you have any technical difficulties, try logging out and log back in. And if doesn't solve the problem, you can watch the presentation on live streaming link on YouTube. So we have sent that link to your email. Thank you very much.
That's great. Thank you, Manjula. So today I'm delighted to introduce you to Dr. Jeff Dusek. He's an assistant professor at Olin College in Needham, Massachusetts in the United States. I had the pleasure of meeting Dr. Dusek 6 years ago when he was a graduate student at MIT and then at Harvard. And my students were studying about the ocean. He was such an inspirational speaker and got the students so curious about ocean engineering. It was amazing. I thought it would be great to have Dr. Dusek speak with you all today during our ocean presentation series that we've had this week. Today, he will discuss his fascinating research in robotics and ocean engineering. So Dr. Dusek, welcome.
All right, well, thank you very much for having me. Let's see if we can get a screen share going here. All right. You should have some slides now. Is that
Yeah.
looking okay?
Yeah, it looks great.
All right, excellent. So thanks, Lorraine, for the intro. I didn't realize it was 6 years ago now that I was in your classroom in Newton. That's a lot of fun. So as was mentioned, my name's Jeff. It's great to meet you all. I am an assistant professor in the mechanical engineering discipline at the Olin College of Engineering, Franklin W. Olin College of Engineering, which is located just outside of Boston. And when I put these slides together yesterday, I didn't include anything really about Olin, but I figured I should probably add at least a map to give you some idea of where we are. So if you know the East Coast of the United States and where Boston is, Olin is a very small engineering-only, undergraduate-only college, just kind of to the southwest of Boston. And we are very close to Wellesley College, which you may have heard of. We do a lot of shared work with them, as well as Babson College, which we basically are right next to. So it's a really fun place to be. Before I start today, I also wanted to mention that so today, June 10th, there is a strike going on in academia to support the Black Lives Matter movement and racial justice. So if you've followed any news in the United States, we're in a bit of a time of great turmoil and reckoning and confronting our privilege. So I wanted to just call out that this strike is happening on today. With this international audience, we wanted to go ahead with this talk, but my lab will be in full support of that strike and shutting down our regularly scheduled research activities today. So wanted to make sure that I mentioned that.
Thank you.
All right, so Lorraine mentioned that I am an ocean engineer by training. So my background is in ocean engineering. And the question that I usually get when I first start talking about ocean engineering is what actually is it? I've had people ask me like, oh, how do you engineer an ocean? It's like, well, it's not quite what we're doing here. And the way I really like this quote from Theodore von Karman, who's, a legend in the fluid dynamics field, but he says, scientists discover the world that exists and engineers create the world that never was. And so when I talk about ocean engineering to folks, I normally say that, most people understand what a marine biologist is, working with natural systems, studying plants and animals that live in the ocean and lakes and such. As an ocean engineer, I kind of look at myself as the person who builds the tools that allow for that sort of research. So while marine biologists work with natural systems, as an ocean engineer, I design mechanical and electrical systems, which end up working in the marine environment. So that's probably maybe the simplest way to think about it. And one of the really cool things about ocean engineering itself, it is an inherently interdisciplinary field of study. So I think about ocean engineering as combining many engineering disciplines, drawing on the content from mechanical engineering and electrical engineering, computer science, material science, and really, bringing them together and placing all those fields into the context of the marine environment. So the marine environment is extremely challenging. It has unique features such as, enhanced corrosion due to being wet and high levels of salt when you're in the ocean. The marine environment is dark and it's challenging and there's a lot of pressure. And so you think about adapting all of these skills from other engineering disciplines and placing them in this context of the ocean. And so when we think about, specific content areas of my formal training and what I try to impart on my students is, there's a high level of engineering math and physics. And personally, I'm an experimental hydrodynamicist, so thinking about fluid flows and how structures interact with water and waves and currents. There's electrical prototyping that happens in the circuitry and computer programming. I think that in modern engineering study, it's almost impossible to not have some level of programming that takes place. Machining, we still build stuff that we're going to place in the ocean, which is fun. And some material science. So I'll talk a little bit about my PhD research, which was building sensors. And so I ended up doing a lot of work with soft materials and doped polymers in order to create various sensors. So I thought it'd be interesting to talk a little bit about, how I ended up as an ocean engineer and an engineering professor at a small undergraduate engineering school. And so on the left side of my slide here is this video that I just pulled off YouTube, but it shows a pipe insulation roller coaster. So it's this foam pipe insulation that you usually put on pipes where I live in New England now. Your pipes freeze in the winter if you're not careful, which is not good. But I remember back when I was in 5th grade, so that would be age 10 or 11, in my science class, we made pipe insulation roller coasters. And that was the moment that I decided I wanted to be an engineer. And now, for a long time, I wanted to design roller coasters, and it turns out only very few people get to do that. But I've also always loved the water. So I grew up in Cleveland, Ohio, so right on the shores of Lake Erie, and grew up sailing and playing with boats. And the picture on the very right is just a few years ago, racing with one of my friends in grad school. But from a very early age, I knew that I wanted to work around the water and on the water and with boats. And so, when I started doing my search of what I wanted to major in college, this thing called ocean engineering popped up, and it was like, yep, that sounds like what's going to be. So, when I was really kind of first entering college, I kind of decided I want to be an ocean engineer with the goal of designing sailboats for the America's Cup. So if you haven't heard of the America's Cup, it is kind of the pinnacle of competitive sailing. Worldwide event. The next one will take place down in New Zealand in a couple of years. And, when I was first starting in ocean engineering, the boats looked like the ones on the left of this slide. So what we call a monohull. So, a single hull, fairly traditional looking boats, although at the time I thought they were kind of the coolest things in the world. It's amazing the evolution that has happened to these boats over even the past, 10 or 12 years. So the photo here in the middle is from the 2013 America's Cup, which took place in San Francisco on the west coast of the United States. And by that point, the boats were fully flying. So these boats are able to travel over the water at about 35 to 40 miles an hour, maybe faster. They're incredible feats of technology. And that just really was motivating to me. And on the far right are the boats that will be used in the next iteration of the America's Cup that's about to take place in New Zealand. And so these are monohulls again, but again, they're flying boats. They're using hydrofoils to produce lift from the interaction of the speed of the boat with the water to lift the entire boat, above the water surface and essentially fly. And again, reaching speeds that you probably wouldn't expect to get on a boat without a motor, especially. Unfortunately, I'm not designing boats for the America's Cup, but that's okay because I feel like I have one of the best jobs in the world right now as a professor at an engineering college. And so I'd say it turned out okay so far. So a little bit more about that progression. I decided to do ocean engineering as my undergraduate, and I attended Florida Atlantic University, which is really cool. So in this picture on the left here, you can see me working on my senior design project. We built an autonomous surface vehicle. So it would drive around the intercoastal waterway and take videos and send them back to a base station. And the joke I often tell, and I don't know if this will resonate well and with the diverse set of languages, but the project kind of consumed me. So both in times and the fact that I'm actually inside the boat here. So after finishing my undergraduate degree, I really felt like I had learned a lot and I was enjoying what I was doing, but I felt like I could learn more. And so I decided to continue on to graduate school. And so I worked on a PhD in ocean and mechanical engineering from MIT, the Massachusetts Institute of Technology, in Boston. So I moved up to Boston and worked in the MIT towing tank. So my advisor, Michael Tranafilo, was there in the middle with some of my lab mates. And this big tank of water was where we spent most of our time. And so we designed instrumentation to use underwater and, dragged them through this water tank and saw how they performed and stuff like that. I spent a lot of time in Singapore during grad school. So we had a lab in Singapore and it was a really fantastic experience. And then from there, I decided I really wanted to continue on this academic quest. And so I took a postdoc at Harvard University. So again, just outside of Boston in the self-organizing systems research group. So with a wonderful advisor named Radhika Nagpal. And in that group, we worked on swarming. So this idea of a bunch of small robots working together. And I was really focusing on underwater swarming. And I'll talk about that as one of the project examples later in this presentation. All right, and so where I am now, so I am at the Olin College of Engineering, and at Olin, I have a lab called the Lair, because everyone wants to have a lair. I mean, why not? When you're growing up, you want to have your evil lair. Well, hopefully it's not very evil. But so I have the Laboratory for Adaptation, Inclusion, and Robotics, which is a great acronym, if I do say so myself. And, the name for this laboratory was very intentional. So we do a lot of work in assistive and adaptive technology, so the adaptation comes from there. It also speaks to our mindset of working with new technologies and adapting them to other purposes. The word inclusion comes from the idea of both having lots of different types of students working for my lab and working on projects, especially in the field of assistive technology, that bring people into science and technology, create devices that help with tasks of daily living, and really work on that inclusion piece. And then robotics, our tool that we use for a lot of our efforts are tools from robotics. So we build small fish robots, we prototype electronics, we work with power wheelchairs. So robotics really ends up being the tool and the mechanism and the vehicle to achieve our goals of adaptation and inclusion. So Olin College is undergraduate only, so all of my research students are undergraduates. And as I said, the laboratory focuses on two primary themes. So we work on assistive and adaptive technology. An example of that is on the far left is a smart power wheelchair that we worked on a couple summers ago. So thinking about adding some sensors and instrumentation to a power wheelchair, not to replace a human driver, but to enhance their performance. So to provide variable levels of help in order for an individual with a disease that maybe is progressing to keep performing at a high level that they want for their daily living. We're also working on storage for power wheelchairs. Right now I have students this summer working on rehabilitative devices for children with cerebral palsy, which is a lot of fun. And then our second theme is marine robotics and sensing, and that's where I'm going to spend the majority of the rest of this presentation, is really talking about the ocean engineering and marine robotics part. So on the right-hand side, just a picture of some of the very small kind of miniature fish robots that we build in the lab. And the miniature robots are great because if you're working with undergraduate students, it's a great way to move them into the marine field in a very approachable and affordable way. So what I'm planning to do over the course of the next, 30 minutes or so will be to talk about 3 different projects that I've worked on in the field of ocean engineering to try to demonstrate the range of the research and the range of the various projects that kind of fall within the umbrella of this field. And so I said earlier that ocean engineering is inherently interdisciplinary, and hopefully, as we talk through some of these projects, it'll demonstrate that there's really a lot going on. So those 3 projects are going to be bio-inspired sensor design. So that was the work that I did at MIT during my PhD. Some bio-inspired swarming. So this was the work that was during my postdoc at Harvard and then continued on a little bit at Olin. And then a new direction of research that we're just starting on in my lab at Olin, working on aquaculture and sensing systems for aquaculture. We'll really talk about how our oceans are really in peril right now, and that sustainable aquaculture is probably going to be necessary for us to continue feeding the world and not killing off everything. All right, so I mentioned that we were going to do bio-inspired sensors. And so one of the areas that I've spent a lot of time is this idea of biomimicry, which is using inspirations from nature and applying them to engineering systems and human problems. So influences from nature can be seen in all sorts of engineering applications. So a couple of photos I have here are, the design of a bullet train, I think in Japan, that, is kind of modeled off of the aerodynamic shape of different types of birds. On the right is this very small car that was modeled off of the shape of a boxfish, which is surprisingly aerohydrodynamic, despite this boxy shape. It moves really well. But there's a lot of other examples of this as well. So you may have heard about various coatings that are based off of shark skin, that are low drag or resist biofouling or various things. Optical flow sensors are based on the eyes from hummingbirds or bees. And then you may have seen videos of various running robots. So, the Robo Cheetah at MIT or the Spot robot from Boston Dynamics. Another example I didn't put on here that I just remembered as well is adhesives based on the fingers of geckos, that can climb up interesting surfaces in variable terrain and stuff like that. So bio-inspiration and biomimicry, we see it a lot in engineering, and it's really drawing on the years and years of evolution that we see in nature and using those lessons for our own systems. So the first project that I want to talk about a little bit is my PhD work, which was on developing lateral inspired sensors. So when you think about working in the ocean, there's really a few problems that you run into when you start thinking about marine robots. Well, one, you can't really see in a lot of cases. So if we look at the picture on the left here, this is an example of turbidity. So water often has a lot of particles that are suspended in it, whether dirt or sand or things like that. And it makes it very challenging to navigate using visual systems like cameras. It also is very dark in the ocean. So as soon as you get below, a certain depth, light really doesn't make it down there. And so again, using visual systems like cameras become very challenging without high-powered lights, which draw a lot of energy from your systems. On the surface, you have waves, which make it hard to see. You really can't hear all that well underwater. So a lot of underwater sensing is based on acoustics, so using sound. And it works generally pretty well, but there are trouble that you run into with noise sources from biological and man-made things. So one of the problems when I was doing work in Singapore is there's snapping shrimp off the coast of Singapore, and they make it really loud, and so it's hard to use some sorts of acoustic mechanisms. And also when you're in shallow water, on the right-hand photo shows this idea of multipathing. So if I'm trying to either communicate or make a map using acoustic means, your sound waves bounce off the seafloor and off the sea surface, and it become really challenging, especially in shallow water, to understand those signals. And it's also just really difficult to communicate. So on the surface, robots typically rely on radio frequency communication, or GPS, or various other systems of that sort, Bluetooth. None of those work underwater. So water absorbs radio frequency signals and attenuates them very quickly. And so, we're on the surface, you might be able to communicate over, hundreds of kilometers. Underwater, you might only be able to communicate for about a half a meter, using some of these RF signals. So it's a really challenging environment. Now, looking to nature, we see fish have this really cool sensory system on the side of their body that they use to accomplish a lot of these things. So in the video on the left-hand side, which is hopefully playing for you, this is a fish called a blind Mexican cavefish. And so these are little fish that live in caves in Mexico, like the name suggests. And those caves are completely dark. So over the years, their eyes have completely atrophied away. So they actually don't have a visual system for navigation. But you can see this little dude just kind of cruising around through this Lego maze very rapidly. And if you were to zoom in, he actually doesn't hit these Legos. And so the question is, okay, if this fish doesn't have eyes, how is it navigating through this maze? And it turns out that fish have a sensory system called the lateral line on the side of their body. And so in the upper right image, that lateral line is outlined in these red dots. And basically, if you look at the lower panel, what the lateral line is a set of little nerve endings that are embedded either on the surface of the skin or underneath the skin that measure flow speed. And so for the neuromasts, or these little nerve endings that are beneath the skin, what you end up happening is if you have a pressure difference along the side of the fish, which can happen due to interactions with flow structures or the presence of obstacles or, a little bug that it wants to eat vibrating somewhere in the water, you actually get this induced flow through these canals, which, kind of tickle the nerve endings, and the fish can feel that. So these nerve endings get deflected by this induced flow. It sends signals up to the brain, and the fish are actually able to navigate and, carry out their behaviors based on essentially seeing the flow structures around them without eyes. And so, as an engineer, we look at this and we go, okay, operating in a marine environment is super challenging. We have trouble seeing, with turbidity and darkness. Maybe we can draw a lesson from this lateral line system that fish have and apply it to our underwater vehicles. So, if you look at the left-hand side of this slide here, we can think about a few different behaviors that fish do that we might be really interested in doing on an underwater robot. So the first one is just, this is our blind Mexican cavefish. You can see that it doesn't have eyes, and it can detect obstacles. And so if we think about an underwater vehicle, being able to detect obstacles so we don't run into things is really important. And being able to detect obstacles in non-ideal conditions, so if it's dark or if there's, a lot of turbidity, that would be really great. So there's an idea. We could object detection, taking that idea from nature and moving it to unmanned vehicles. I'll talk a little more about cooperative behaviors later, but fish do this incredible thing where they form into huge schools. So in that middle image on the left-hand side, that's called a bait ball. But basically that is hundreds or thousands of fish all swimming together in a cooperative motion in a coordinated way, which can help them stay safe from predators or save energy due to their swimming. And that's something that we might want to do with robots as well. So utilizing multiple robots to do cooperative behaviors would be really great. And doing that in a low cost and simple way. So relying on sensory systems would be awesome. And then the last one is just organism tracking. So fish use the lateral line sensor to track prey. With our underwater robots, we might not be tracking prey, but you could imagine following after a whale in order to see how it interacts with its environment and do some sort of biological research. So this idea of tracking after an organism and following it as it moves around is really powerful for scientific uses. So basically the work that I did over the course of my PhD was trying to change the paradigm for underwater sensors from what you see on the left, which are large, expensive stainless steel, rigid sensors, to what you see on the right, and these are pressure sensors, to what you see on the right, which are soft and flexible and waterproof sensors based on a material called polydimethylsiloxane, which we typically refer to as silicone. So silicone is, really common. It's very inexpensive. It's waterproof. It's flexible. It's easy to manufacture. And it turns out that if you take silicone and you embed within the silicone conductive particles, you can create a material that is what we call piezoresistive. And all that means is that the resistance of the material, the electrical resistance, changes as you press on it. So basically what happens is, if we look at the left-hand side here, this is just a little cartoon of what's happening inside this material, is basically you have this bulk matrix. So this PDMS silicone foam, which is the light gray, and embedded inside of that are all these little particles of this material we call carbon black, which is it's a petroleum byproduct and it's conductive. And what happens is you push down on this material, more of these conductive particles come in contact with each other. And so basically the resistance of the material goes down. And so that's great. That means that if I apply pressure to my material, the resistance changes. So right there we have a sensor. So we can say, okay, if I'm measuring the voltage through my sensor, as I push on it, resistance changes, my voltage is going to change. And we can measure pressure, we can measure force. So that's cool, really cool. So what I show on the right is, the sensors that I ended up building. So these were arrays, not single sensors, but 4x1 arrays that were quite small. So 80 by 20 millimeters, and more importantly, very thin. So in this case, I made multiple different thicknesses, but this particular one is 7.8 millimeters. So very thin sensors that then can basically be glued onto the side of marine vehicles or foils or various things, submarines, in order to have that sensory mechanism similar to what fish have. And so the question is, how do you test this? Well, you test it like a fish would. So on the left-hand side, which the video is being a little, there we go. Video should be playing now. Try playing that again. This is a fish in a water flume. So the water is flowing from bottom to top here. And the fish is in what we call the wake of this D-shaped cylinder. And fish tend to hide behind obstacles because they can save their swimming energy by essentially utilizing the flow created by these obstacles. And we call that a von Karman vortex street. It's a very ubiquitous flow in fluids. And so we noticed that fish really take advantage of this. So we decided we were going to test the sensors in a similar way. So on the right-hand side is a foil being towed through the towing tank at MIT. And my sensors are glued onto the side of the foil, kind of right below the water line. And we basically towed this sensor and the flow created by this upstream cylinder, and we were able to detect the presence of these flow structures, just like a fish would. And so for us, that showed, okay, cool, the sensors work. And potentially we could then use them to inform, motions by underwater vehicles and different things like that. Didn't get quite that far during my PhD. I wanted to graduate at some point. But it was a really promising first step to say, hey, we can actually start seeing the fluids like a fish does. All right. So that was kind of the work on bio-inspired soft sensors. We're going to, stick to this theme of bio-inspiration, but kind of change course a little bit here and talk about collective behaviors and swarming. So when I started my work at the Self-Organizing Systems Research Lab at Harvard, we really wanted to focus on this idea of collective or cooperative behaviors. And really the principle behind cooperative behaviors is that a group collective can often achieve things that a single individual cannot. And I think especially with a lot of the things that are going on in the world today, that's actually a really important message, even beyond engineering systems. But if you look at the two pictures on the left-hand side of this slide, you see that, these ants want to kind of go from the ground up to this leaf. And individually, they can do that. They're too small. But when a group of ants works together, they can actually form bridges out of their own bodies and able to, move across this gap that's way too large for any one of them. And the interesting thing with ants is that they really don't have a leader that is telling each individual ant where to go to create this bridge. Instead, each ant is following a set of very simple rules. And these behaviors actually emerge out of that simple set of rules. So that's cool. And then on the right, this is geese flying in this V formation, working together in order to reduce the amount of energy needed to fly over very long distances. And so we see these collective or cooperative behaviors in many different parts of nature. And we would like to do some of them with our robotic systems. So at Harvard, we were working on various different types of cooperative behaviors. So I just included a couple examples here. These are not projects that I worked on necessarily, but things that were from the lab. So at the top is a set of robots called termies. So these are robots that were inspired by termites and how termites build these really large and intricate termite mounds. And I don't know if this video is going to play. It seems like it's getting hung up here. But basically the idea is that these termies robots work together to build structures. So it's multiple robots. No one is controlling them, but they move around and they can build structures with multiple robots working together. So that's the termies robots. And so the idea here is, in the future, we could have teams of robots that are building structures rapidly and without the intervention by humans. So this could be really useful in all sorts of parts of the world, or for disaster relief. You can think of lots of opportunities where collective building of structures could be really valuable. Pause that one. On the bottom is a project called the Kilobots. So this was really investigating collective behaviors in very large scale systems. So if we look at I'll play this video. So this swarm is 1,024 robots. And they use a very simple communication method of bouncing infrared light off of the tabletop to talk to each other using LEDs and photodiodes. And with this 1,000 robot swarm, they can work together to do very simple behaviors like, building shapes. And again, the video here is being taken overhead, but there's nothing controlling each of these robots individually. Every robot in this swarm is following the same set of rules, and these intricate shapes and behaviors emerge from the following of that set of rules. So there's no centralized control. And I think that's the really key part to think about when we talk about collective behaviors by robotic systems. So right now you might be asking the question, hey Jeff, you're an ocean engineer. You built sensors for your PhD. What are you doing at a Swarm Robotics lab? And that's a great question. So when I joined the lab at Harvard, what we really wanted to work on was doing swarming underwater. So basically thinking about schools of fish. So in nature, fish schools are a biological behavior that has some really nice benefits for the fish. So if this video on the left will work, doesn't appear to want to, but if it was working, it would show basically a shark attacking this little fish in the middle, which is sad for that fish. But in nature, fish schooling is often used as a predator avoidance mechanism. So when you have a bunch of fish swimming in coordinated swarms, it makes it much harder for a predator to attack any single individual. So it's a survival mechanism by these fish. It also leads to energy savings. So when you have a bunch of fish swimming together, each individual fish is actually using less energy in order to swim. So an example of that would be if you watch cycling, there's the idea of the peloton, right? So a bunch of cyclists riding together, and each individual cyclist within that peloton is actually using less energy because there's less drag from overcoming the aerodynamic drag of the wind, because they're riding essentially in the wake of the cyclists in front of them. And so when we start thinking about underwater robots, doing similar collective behaviors could be really beneficial. So energy savings. So if we want to move across a long distance with our underwater robots, moving in a school so that you don't use as much energy would be really great. The other ones I kind of show on the bottom examples is this idea of underwater search. So one of the main reasons that we use underwater robots is for mapping and search sort of missions. So, one of the examples that I've talked about in the past is, when you have something like an airline crash and you're searching for a black box. The ocean is a very large place. And with an underwater vehicle, you're making a trade-off between how much you can see on the bottom by how close you fly to it, essentially, and how much area you can cover. So on the left-hand side, this is the typical search pattern that you use with an underwater robot. We refer to it as, mowing the lawn, this kind of moving in a very set geometric way. If we could instead have a swarm of underwater vehicles all doing their own independent searches in a much more non-structured way, you can potentially cover a much greater area faster, which could be really important if this is a search and rescue mission, or finding a leaking oil well. There's any number of examples that you could talk about. So when I was at Harvard, we worked on building this little underwater robot that we would use for swarming. So it's shown here. So this is a very inexpensive robot. It's about 10 centimeters long. So you have a US penny next to it on the right-hand side for scale. But it's a very capable robot. So it can maneuver in with 6 degrees of freedom in full three-dimensional space. It has an LED and photodiode, so it can move towards light sources. It has a pressure sensor in order to regulate its depth. And the propulsion is provided by flapping fins. And it's interesting, we didn't actually set out to build an underwater robot that looked like a fish. That actually wasn't the goal. But it turns out that using a flapping fin like a fish does to maneuver underwater is actually really efficient, which kind of makes sense because fish have, evolved over thousands of years. So the propulsion mechanism here, if you look at, above the pectoral fin, you see is what we call a magnet in coil actuator. So we have a coil of wire, and inside of that coil is a magnet on a hinge. And as you change the direction of the current through the coil, it creates a magnetic field, which causes these fins to flap back and forth. And those actuators are about 10 cents a piece when you order the coils in bulk. So it creates a really inexpensive way to create a completely waterproof underwater actuator. Hopefully this video works. So this just shows our little robot, swimming around. It's not extremely fast, but it's kind of cute in my opinion. But it's a little swimming robot. And you see at real speed, it swims at about 1 body length per second, but it's a very small body length, so it's not particularly fast. But we can swim in a straight line, we can swim in circles, we can swim in squares, we can hover at a particular depth, so use our pressure sensor to decide what depth we're at, and then use feedback control in order to regulate depth. We can dive up and down between depths. So that can be really important if you're trying to, say, survey the full volume of an underwater area. So we can regulate our depth. We can swim squares. So we have a IMU inside the robot that keeps track of its position and how much it's turning. So we can have it swim particular patterns. And we can also do things like we can swim squares at different depths. So swim a square at a certain depth, rise up a little bit. It's a positively buoyant robot. Rise up a little bit more, swim another square. And so again, this is an example of how you could, basically take measurements over a full volume of water if you were doing something like environmental monitoring. And one of the things that I worked on a lot when I was part of this project was doing visual tracking of the robot in 3 dimensions. And so whenever you do experiments, you want to make sure that you need to have some way of assessing the experiment. So we worked on being able to track the robot in 3 dimensions. In this part of the video, we're showing how the fish can basically swim back and forth between light sources. So it has a photodiode on the front of the fish. And as we turn lights on and off, it'll swim towards the light. And so this could be a way of, one of the behaviors in collective robotics is getting a bunch of robots to come together as a group. And so one way you could imagine doing that is by having a really bright light that all the fish then, swim towards. And again, spirals and squares and search patterns, just demonstrating that a very, very small 10-centimeter robot actually has quite a bit of capability. And so that was all work that was done over at Harvard during my postdoc. But when I came to Olin College, we brought this idea of very small, inexpensive underwater robots with us. But instead, we wanted to work on this idea of undulatory swimming. So again, bringing this idea of bioinspiration back. And in nature, fish swim in this undulatory motion. So they flap their tail, but the whole body moves kind of like a sine wave. And this is, in the middle here is an image from a really nice numerical study that looked at the swimming of tuna. And you see that, the whole body flaps and it generates these strong vertical structures in the wake of the body, which cause very efficient swimming. And I find fish swimming to be extremely beautiful. When I went to the Monterey Bay Aquarium a few years ago, I was at the deep ocean tank, and I remember just watching the tuna swim and just being absolutely fascinated by just how efficient and beautiful they are as they swim. So on the right-hand side are some little robots we've been working on at Olin with the undergraduate students, thinking about, instead of having a single flapping tail like our Harvard robot, having the motion of the fish come from multiple joints within the robot, and the entire fish doing this undulatory sinusoidal type of swimming in order to increase efficiency. So these are still kind of on the 10 to 20 centimeter sort of scale. They're 3D printed. So, these fish use very low cost and very simple sort of hardware. So they're 3D printed bodies. We use our, Arduino Pro Minis, which are, inexpensive microcontrollers. And again, these robots are powered using this magnet in coil, or what we call a MIC actuator. So very low cost actuators and waterproof. And so on the upper right here, you'll see kind of a final of these simple robots. And in this case, they're not autonomous, they're tethered, but it's a way for us to start, investigating this idea of multi-jointed swimming. So just a couple images of what that looks like. So my student Katya did some great work on, doing experiments in a small water tank and using overhead cameras with these little blue markers to track this undulatory swimming motion, and then looking at joint angles. And so this was all open loop swimming, so we didn't have a feedback controller in the fish, but we did find we got some pretty nice swimming performance with this undulatory motion. We also found that we have a long way to go to get anywhere close to the efficiency of actual fish. So we were able to achieve about a little over a body length per second, but fish can do much, much, much faster than that. So undulatory swimming is excellent, and there's been a lot of work in it, but most at large scale and very expensive robots. So we'll continue busting away at this for a little while longer. So we're getting towards the end here, but I wanted to follow up with one last thing, which is talk a little bit about aquaculture. So many of you have probably seen the UN Sustainable Development Goals. And so goal 14 talks about life below water. And one of the goals outlined there, 14.A, not sure why they went with A instead of a number, but anyways, is really talking about developing research capacity and marine technology, and thinking about how marine technology can improve ocean health and enhance marine biodiversity, especially in developing countries. And so at Olin College, we really are trying to train engineers that are going to make a difference in the world. And so the UN Sustainability Goals are something that really resonate with us. And so I'm thinking about, trying to move my lab in the directions of focusing on sustainable marine technologies. And a couple of stats here that I pulled out of some of these UN reports. So, over 3 billion people depend on the marine and coastal biodiversity for their livelihood, either directly through fishing or indirectly through other industries that are related. 33% of our marine fish stocks in 2015 are being harvested at unsustainable levels. 60% are basically at their max sustainable level. So we're in a bit of a crisis when it comes to fishing in the world right now. We're essentially exploiting our oceans and pulling out way too much fish. And as global populations continue to rise, it's going to be a problem. Because of climate change, not only are we pulling more fish out of the ocean, but the ocean is actually getting less productive. So as global ocean temperatures rise, acidification increases, not only are there, we're not only grabbing more fish, but there's just less fish there to grab. And so this is an existential threat to both the world and to people. And so I pulled this quote out of a paper. I'm not going to read it completely, but basically it's saying that the Food and Agriculture Organization at the UN is really saying that we're overfishing, and as our population rises, that's going to be even more of a problem. So the plot on the right shows, so on the x-axis on the bottom here, this is from 1975 to 2015, and the orange in the top is the proportion of global fish that are overfished, and you can see that is increasing over the course of time. So the question is, all right, global populations are increasing. We're also eating more seafood than we have ever in the past. And our productivity of the oceans is decreasing. How do we basically deal with those conflicting problems? And I think one of the solutions is aquaculture. So we need to start doing intentional farming of fish and other seafood stocks in order to continue satisfying the needs of a growing world population. And so the figure on the left shows that aquaculture is increasing year on year, where the production of capture fish is either leveling off or decreasing because of that decrease in productivity of the ocean. And the plot on the right, the interesting one is the red line, which just shows the consumption by humans of seafood, and in this case, fish in particular, over time. So not only are there more people, but more people are eating more seafood. And so when we talk about aquaculture, a lot of people think about fish farming onshore, so in ponds. And right now, freshwater sort of pond-based aquaculture makes up the largest proportion of what's happening worldwide. But the future of aquaculture, in my opinion, really lies in offshore practices. So moving fish farming further away from shore into deep and nutrient-rich waters, and so strong currents bring in natural nutrients to the fish and keep them healthier, while also dispersing the byproducts and reducing the environmental impact of having these fish farms. And so on the left is a fully submerged fish cage off the coast of Hawaii. On the right is a plot showing these kind of various types of farms. And it's really going to be a holistic ecosystem. So raising young fish on shore, growing kelp and shellfish near shore, and then thinking about doing these fully submerged cages far away from shore in order to take advantage of the existing productivity further away from our coasts. When we think about fish farming, it's a really hard challenge, especially as you move offshore. So there's a lot of engineering opportunities here. So if we think about building large-scale offshore fish farms, we need robust structures. The ocean's a really hard place to work. There's waves and currents that destroy things. We need advanced sensing. We need about the health of our fish. We need to feed and maintain the fish stocks autonomously. We need to be able to communicate in real time to understand, when we need to harvest. We also really need to understand the environmental impact of our actions. And so there's been just a few studies so far looking at the environmental impact of offshore aquaculture. And the good news is so far that it's found it's quite safe if you have these cages off in strong currents and away from shore. So this was a study done by the University of Miami, studying a fish farm that's off the coast, about 8 miles off the coast of Panama. And they found that, if they sampled upstream of the cages and downstreams of the cages, the nutrient levels were actually very similar. So these offshore submerged cages have a lot of promise for a future where we're producing large amounts of high quality protein to feed the world while also not impacting the environment. But we can't just take this for granted. We actually need to build underwater robots and sensors to make sure that our fish are healthy and that we're not impacting the broader environment. And so in my lab, we now have funding from MITC grant to work on sensing solutions for offshore aquaculture. So I have 4 students working on this summer, where we're going to be building devices that you can basically attach onto cables that already exist within these fish farms in order to measure fish health and environmental impact. And so I feel like that's the next phase of my journey through ocean engineering, is to work on this question of sustainable aquaculture to address some of the challenges we face in the world. So with that, I just want a couple acknowledgements. So the MIT towing tank and my PhD advisor, Professor Michael Tranafilo, who's an amazing researcher. The Self-Organizing Systems Research Lab at Harvard, and Professor Radhika Nagpal, who's just a fantastic human being and an amazing mentor. And now my students who work for me in the Lateral lab at Olin College, an incredible group of young people that I enjoy hanging out with and working and going to brunch, and they're a great group. And with that, I will open it up for questions. And I think I'm going to stop screen sharing.
Sure.
So y'all can see me. That's me sailing off of Hampton Beach, New Hampshire a few summers ago. But we can always, bring back other slides if needed.
Wow, that's
All right.
excellent presentation. Thank you so much for that.
Oh, absolutely, yeah.
It was really fascinating. You took us through the whole journey here. That was great. If there's anybody who has a question, you can type it into the chat, or you can put your hand up and we can call on you.
Yeah, Gina.
Gina has a question, I think. So Gina, you can ask the question now.
Yes, hello from all of us in the UAE. I apologize, my son was supposed to be here on the session. He's really interested in marine biology and robotics. So he had a question. A couple of years back, he was working on life below water on sustainable development goals, and he presented a project where he wanted to address the threat that sea animals are facing with regards to being killed due to traffic in the ocean. Yeah. And he created a kind of a project where below the boat, it had a kind of robotic device that would detect the echolocation, from sea animals, and send out of radiations to block animals from getting into the path of a huge boat, or maybe a hovercraft or something. So because we've noticed that nothing has been done so far, the number of deaths are increasing, with the traffic, with the logistics, and with the sea fisheries, and a lot other transportation in the ocean. So the question is, why isn't technology advancing to help the animals who don't have a voice? And now that the UN goals are in place, why is there no active funding towards that cause? If you can create a low cost device and make it mandatory for all boats.
Yeah, that's a great question, and I think that it's probably not a technology problem, right? It's a social and economic problem in a lot of ways. So, do we have the technology to identify marine creatures and potentially, emit some sort of thing to warn them and keep them away? Yeah, probably. I have some colleagues who were working on detecting the presence of whales based on the infrared signature of their plume, when they come up to the surface and breathe. I think, if you ask the question of why those aren't on ships, it's an economics thing. It's, we as engaged researchers and people who care about sustainability need to somehow show that the economic cost of adding a device to your ship, which will slightly decrease the profit margins, is worth it, right? And so I don't know if I have a great answer for you, aside from saying it's an advocacy question. It's a convincing regulatory bodies that this actually is important. It's, lowering our dependence on, marine transport of petroleum. It's any number of things that tie into the full sustainability ecosystem. And I think a lot of it starts from advocacy, social change, and then regulatory change. For those in the US, I would say it's a case of we need to vote for people who care about this stuff. Yeah. Right. And it's an awesome question. And I wish I had an answer that would say, oh, the challenge is this particular, technology thing that if we just had a little bit more money, we could solve. But in this case, I really don't think that's what it is. It's the same reason why we don't have, marine renewable energy. It's that it's expensive to develop, and you need to demonstrate that there's a need for it and change hearts and minds in a lot of ways. So, yeah, advocate. Okay. Talk to your elected officials. That sort of thing.
All right. Thank you.
Absolutely.
Thank you. Let's see. We have many questions here. Bulan, do you want to say your question out loud?
Okay, why not? It's an honor. Do you hear me?
Yes, you can turn your cam on if you'd like.
Oh, okay, no problem. Okay, my question is, as you see on the chat part, how long have you been studying on this project? And how long more will you be doing this till you get your desired results? The first question.
Yeah, that's a great question. I mean, so it kind of depends. Like my PhD work on the flexible sensors, that took a while. I was a student at MIT for for a pretty long time. So I think it was about 6 years total of between my master's and PhD and working on slightly different things. The new project on the aquaculture is brand new. So that just started in February. And so I had students working on the early phases of that project within a robotic systems class that we were teaching during the spring semester at the college. Unfortunately, about halfway through that class, we all had to leave campus and, due to the coronavirus pandemic. But I have students working on it this summer. We still aren't on campus, so they're working remotely from their individual homes. So it'll be really interesting to see how much we get done this summer. I've never had summer research where my students are in literally all across the country and working in their houses. So that's initially a 2-year grant. It'll probably be extended a little bit. And honestly, the sustainable aquaculture is a field that I could imagine spending a good portion of my career working on, because I really do feel that preserving the oceans and allowing natural fish stocks to renew is going to be dependent on us thinking of creative ways to harvest fish in other ways. So how do I know when we're successful, what the desired result is? It's incremental. right? So in the first stage of the project, it's going to be, okay, can we build a robot that can climb up and down ropes underwater while collecting sensor data? And that's fairly easy to evaluate. We'll be able to do some measurements of that. But again, similar to the previous question, the bigger goal is how do you really create systematic change? And that is much harder and much longer and much harder to evaluate. So I don't know if that actually answered your question, but it's going to be a process.
Oh, okay. Can you tell me, and not an exact, but a day or a date or a time that you can finish everything about the project?
That would be.
Simply no. No, I mean, we have incremental goals that we'll work towards, but the beautiful thing about research is that over the course of the project, we are going to learn the things that we don't even know at this point, right? So, you write a project proposal saying, hey, over the next 2 years, these are the things that we're going to produce. This is the timeline. I don't know if that's actually where we're going to end up, because I think there's so much that we might discover along the way that what our final product looks like is probably going to be fairly different from what it was when we started. So,
okay. What? Sorry.
Go ahead. No, go ahead.
Okay. Why I am asking this question is that I really wonder that if you are going to finish the project with the students you started with, or others are going to come and come and come. I wonder about this process. This is why I'm asking this question.
Yeah, it's a great question. It will likely be multiple students over the years, right? Especially for undergraduate students. It's not like, if I had a PhD student that would be there for 5 or 6 years. That's not the case. Typically with my undergraduate students, they'll work for me during the semester, or maybe they'll work over the course of the summer. But, the students that I have this summer, next summer, they might decide to do an internship in industry, which is awesome. It's great that they see that variety of opportunities that are available for them. And I highly encourage them to do that. So with an undergraduate research lab, there's fairly high turnover. And so the important thing is to create a culture within the lab that allows, students to enter and immediately feel like they're being productive, and mentorship from the older students. And that's something that I've only been at Olin for 3 years, but that's a continual thing I'm trying to work on, is how we can influence the culture of science more broadly.
Yeah,
Thank you for your answer. Thanks. I'm stunned by the job you are doing and your students. Thank you.
Yes,
the students make me look good.
Dr.
Thanks.
Jeff, I have 2 questions today. First one is, so what are the transmission media that you are using inside the ocean that you need to communicate between objects? Now that we are using microwaves, maybe infrared and radio waves. So what are the difficulties that you are facing selecting these transmission media?
Yeah, it's a great question. So I actually have a student working on that. Sorry, Greyhound coming over to say hi. I have students working on that this summer as one of the parts of our project. So the kind of standard communication method in most underwater applications is acoustic. So the thing with working underwater is signals are attenuated, so their strength decreases very quickly. And higher frequencies attenuate faster than lower frequencies. So things like radio frequency and Bluetooth are up at like 2.4 gigahertz and frequency, and so they attenuate quite rapidly underwater. So again, on the order of, a couple meters, maybe. If you use much lower frequencies down into the, maybe kilohertz, so they're much longer wavelengths and lower frequencies, which is what you get with acoustics. You can actually get transmission over, thousands of kilometers. So, and actually within the ocean, there's regions where sound transmits even better, because it essentially bounces between various thermoclines and variations in density. So like whales actually communicate over extremely long distances underwater using sound because they're lower frequency, long wavelength sort of signals. Now, when it comes to our systems, there's trade-offs. So acoustics are awesome, but they tend to create those low frequency, long wavelength signals, they consume a lot of power. And so to use acoustic communication, and they tend to be kind of expensive. So when we're trying to do lower cost robots, we've been looking into alternative forms of communication. So one of the things that you can use is actually modulated light. So thinking about flashing LEDs in very particular sequences and then detecting them on the other end. So an example of this would be if you've ever used the remote control for a TV. So it's using modulated infrared light in order to communicate. Instead of using infrared, we would use essentially light in the blue spectrum, because blue, so that wavelength transmits really well underwater, which is why we see the ocean as blue. And so if you use a blue or a blue-green LED, you can actually get transmission over fairly long distances underwater, and you can actually get fairly high bandwidth by how you kind of encode messages within that light. We're also looking into RF, but just over short distances. So it's really application dependent.
Interesting. I have a question that came from Adel Kassa, who's in Tunisia. And I'm not sure I'm going to get this right, so you'll have to help me. It says, how do you see how AI and computer vision will be used in your field?
Oh, that's a fantastic question. Okay. So I have some students thinking about that a little bit right now. So we're thinking about it right now in terms of the aquaculture application. So for a fish farmer, one of the things that they really want to understand is how many fish there are and how big there are. Because the amount of fish relates to profit in a very real sense, but it also means that like you can determine how much food you need to use based on how quickly the fish are growing and stuff like that. And so one of the options we're looking into is using computer vision techniques. So basically mounting a camera on our underwater vehicle and being able to, recognize fish, understand how big they are, get assessments for the total number of fish in a cage, stuff like that. And there will probably be some amount of machine learning that goes into essentially training the classifiers to say like, yes, that is something that we care about, or no, it's not. I've also used machine vision just in the sense of like evaluating underwater robots. So I showed the video of the little fish swimming in that pool at Harvard, and we used a set of cameras in order to identify the location of the fish, how fast it was swimming, the angle through which it was turning, stuff like that, in order to essentially calibrate the internal sensors on the robot with an external ground truth sort of system. I mean, I have friends who have worked in using computer vision to assess the health of reefs. So thinking about, as reefs get damaged due to ocean acidification and sea temperature rise, understanding how much reef, how much is getting killed off, the health of reefs, stuff like that. And that's another place where imaging techniques can be super valuable. So yeah, there's a lot of places that it could be used for sure.
Great. There was a question from Rox, and he put it in the chat, but he said the audio is a problem. So he's listening to it, I believe, on YouTube. He said, can we use an EV3 robot underwater?
So I'm not particularly familiar with the EV3, but I saw that question. So I did a quick web search, and it looks like they're the Lego Mindstorms.
Yeah, right.
I think the answer would be maybe. I don't know for sure. Would certainly any areas or places where water could get into the controller. The sensors, it looks like the proximity sensor is infrared based, that might work over very short distances, but not over very long, because again, infrared gets absorbed very quickly in fluids.
So I guess he wants to know, how can he waterproof his EV3 motors and sensors?
Yeah, I mean, one way to do it would be to, to put the like the brain part inside a waterproof container,
Okay.
and then just make sure that like any wires are sealed as they exit the container. So we've used even things as simple as like, Tupperware, like lunch sort of containers,
Right.
Sandwich containers and stuff like that work okay. The other thing that you can sometimes do, it's a little bit more permanent, is you can actually encapsulate things completely within silicone. So think about, you get a two-part silicone, and actually you embed the entire electronics within the silicone. And so that keeps water from getting in. But there's some tricks to doing that. So I don't have a great feel for the EV3s in particular.
Okay.
But we could maybe chat offline.
Yeah. Well, thank you on that.
Yeah.
Let me see if there's any other questions here that are here. I'd love for you to know can people turn their cams on now? Or did you have it? Or this is Buelan. Can people turn their cams on? We have people from, let's see, South Africa. I have a person here from Lesotho. We've got from the UAE, from Turkey. Romania is in the Italy,
cool.
Pakistan, South Africa, Nepal, Tunisia. Yeah, so there's quite a few. If you turn your cam on,
Gotta love modern technology.
yeah, it really can unify a group of people from so many different places and time zones. It's really incredible.
That's very cool.
Yeah.
Nepal is definitely one of the places I want to visit.
Yeah. He was excited to.
Well, if there are any other final questions?
Any other questions anybody has? Any on the chat? Anybody? No. I think you've done a great job of sharing with us, and so thank you. It's wonderful. Oh, Gina, you had a question?
Oh, there's a Gina. Yeah.
Yes. If my son wants to, ask you some questions, is there some mode of communication that we can have between you and him? Because he's pretty interested in robotics and marine biology.
Yeah. So I just put my email address into the chat. So if you want to follow up by email, that's great. Or if there's a question now, I'm happy to answer it as well. I might be slightly slow responding to emails. I'll do the best I can. But things are a little wild. Things are a little wild right now. But I will do my best. So
that's really great. Great. So, Manjula, do you want to?
All right.
Yeah. So, Dr. Dusek, thank you very much for your amazing presentation today. I'm really amazed. And thank you everyone in the room and on the YouTube link for joining with us today. And I think that you agree this is an incredible, amazing presentation and the robotic session. So this video will be shared by so many students in Sri Lanka in engineering faculty. So I have so many students in universities in Sri Lanka. They are going to share this video and get the knowledge that you have shared in this session today. Thank you very much, Dr. Dusek. Thank you very much.
Yeah, thank you. I really appreciate your coming in.
Thank you very much. Thank you for the invite. It was fun being here.
Okay.
All right. Have a great day,
Yeah,
everyone.
take care.
Bye.
Bye-bye now.
Bye-bye.
Manjula, is there a way to take the text, or is there a way to copy the text?
Yeah, I will get it.
Because I think there were some comments and things that he might want to enjoy later.
Okay, I will take some screenshot here.
So
Don't close the room.
Oh, I'm not closing the room.
Yeah.